Good morning, everyone, and welcome to the IBM Qiskit Live Quantum Seminar Series. In just a minute, I'll be very thrilled to roll out here this week's seminar with Michael Gullans. I'm so glad you could join us on time. Before we begin, we always like to give everyone just about a minute or two to tune into the live stream. And we always like to begin with one of our favorite questions, such as, where are you folks tuning in from? I should also mention congratulations to everyone who finished and completed the Qiskit Global Summer School. I had a real pleasure meeting and answering many of your questions on quantum noise. And it's good to always see some of you here in the seminar series as well. You can reply to those questions in the comment chat box here on YouTube, which is located somewhere on your screen above, right, left, or below. And that is the same place where you can ask questions live of Michael during this seminar, during this talk. Now, you can always go back and rewatch the seminar, especially get a heads up on what's coming up by subscribing to Qiskit. But you can always have these live discussions with each other and with myself and the speaker, Michael, during the Friday noon time. So folks, I think with that, it's time that we get to it. Today, I have the special pleasure and privilege of hosting Michael Gullans from NIST QUIX and the University of Maryland on neural network decoders of measurement-induced phase transitions. Michael received his PhD from Harvard in 2013. He was an NRC postdoc at NIST, then a postdoc at Princeton University prior to rejoining QUIX in 2020. Michael is a fellow at the Joint Center for Quantum Information and Computer Science, QUIX, a physicist at the National Institute of Standards and Technology, NIST, and an adjunct assistant professor in the Department of Physics and Computer Science at UMD College Park. With that, Michael, it's a pleasure to have you here. How are you today?
I'm doing great. Thanks so much for having me.
All right, it's wonderful. Last question before you take it away for us. Where are you tuning in from today?
Today I'm in my office at University of Maryland.
All right. Well, we're glad to have you, and the stage is yours.
Thank you. Okay, so you're seeing my slides. Great. Okay, so yes, I'm Michael Gullans, as you heard. So today I'm going to tell you about this topic of measurement-induced phase transitions, and all the first part, neural network decoders, I'll come to at the end of the talk, but most of the talk I'll give you a somewhat broader introduction to the topic. And yeah, so let's get started. Okay, so yeah, let me start off by thanking my collaborators on this topic. So this is a project that got going during my postdoc with David Hughes, and I'll tell you about how we came to understand this problem in these two papers, our perspective on these problems. And then another exciting development is we were able to study this phase transition in an ion trap system, and I'll tell you about what we learned from that work, and that's collaboration with Crystal Noel and my student Pradeep, and then in Chris Monroe's group. And then finally, the work on neural network decoders is sort of a new direction for me that started from a collaboration with Mohammed Hafizi at University of Maryland, where we're trying to use machine learning tools to understand this phase transition. So I'll take you through all these works. Okay, so just to set the stage for the types of problems that I've considered largely throughout my career is what I call these monitored quantum systems. And so the general setup that we have in mind, and it has this rather complicated structure, but in some sense all these ingredients will be needed or important in the physics. But so you have this essential ingredient is you have some many-body quantum system with its own internal Hamiltonian, but it's also an open quantum system. So it's coupled to an environment which is uncontrolled, so that adds noise to the system. And then there's the other aspect that we're very interested in is these sort of controlled parts of the environment. So you can drive the system, and especially in the context of this talk, we'll be exploring this idea of making measurements, quantum measurements of the system, which give you classical data about the quantum system, and then ultimately using that for feedback. So the way we think about this is that, the sort of quantum physics comes because there's a quantum input state to the system, many-body quantum state, and then the output state is also a quantum state. That's what we're going to be probing, but it's labeled by these measurement records. So this is sort of classical data about the system. And so just to give you a more concrete sense for this type of physics, I wanted to take you through some of the recent experimental work in this area. And actually, David and I were very inspired by this experiment by Zlatko that was published a few years ago about which I'll take you through a little bit, but it was about observing quantum jumps in real time. So seeing these quantum trajectories I alluded to on the last slide. So I'm very happy to sort of come back and see Zlatko and what he's working on today. So the basic setup that was considered here is they had a 3-level quantum system formed from 2 superconducting qubits, and it had this special structure that there was a ground state, a dark state, and a bright state. So this state emits many photons when it's excited, and this sort of emits photons at a lower rate. And so by cycling these transitions, you can see the dynamics of these states. And if you were to just drive the system without making measurements, so here you're sort of counting photons coming out of the system, it would sort of evolve to a steady state density matrix, which is rather simple. It's just a 3-level matrix. But when you start recording this measurement data, you get this much richer dynamics, which is an example of which is shown here. So what they're able to do in real time is basically monitor which state this 3-level quantum system is in, and you can see these jumps between the bright and the ground state. That's the blue and the gray, and then there's intermittent periods where the system actually transitions to the dark state, and you don't see any counts. And what was fascinating about this experiment is that they were able to actually catch signatures of this transition and then use feedback to reverse it. So this is really this experiment really inspired David and I to think of this as physically relevant systems, these type of quantum trajectories, and really explore it more in the context of extended many-body systems, not just in time. So this is a many-body system in time, but also in space. So the other natural setting where monitored systems arise and are quite topical currently is in the context of quantum error correction. So here I'm showing an example of an implementation of the surface code by Andreas Walraf's groups at ETH. And here what you should have in mind is more like a conventional quantum circuit with multiple quantum gates, and then sort of they do these syndrome measurements to correct errors, and then the feedback is using the measurement data to correct the errors in the system. This is an example of the device, so you can see that these are really starting to become large-scale systems where people can explore this physics. And then the other example of this type of system, which will be featured in this talk, is an ion trap system. And so here I'm taking an example from Chris Monroe's group. So this is the system. It's in a box to sort of protect it from light, not because there's any secrets in there. And then the basic setup is you have an ion chain, and then you essentially each of these little blue dots is a ytterbium ion, which can be individually addressed and controlled. And one of the unique features of this system, which can be exploited, is that you can basically do entangling gates between any pair of ions in the system, and so it has this long range connectivity. And then they also have individual addressing and then individual readout, which is important for this monitoring the system and making connections to quantum error correction. Right, so in these three examples, I sort of highlighted these sort of systems being explored by academic groups. There's also, of course, amazing progress on this in industry, especially in IBM and other companies. But here I was focusing on the academic work. Okay, so one of the exciting aspects of these monitored quantum systems is they have these very sort of natural connections to machine learning problems, which I'll explore sort of at the end of the talk. But just to give a high-level motivation for that, you can think of this as this problem of learning from quantum data. And there's been a lot of nice work on this, and I just want to highlight two of these recent papers, which have been quite inspiring for the community. And so, but what we're really with the advent of these experimental quantum systems, it's starting to raise questions about what's the power of data obtained from quantum systems. So here on the left, I'm showing an example of a complexity theory result in computational complexity theory, showing a separation between say classical algorithms and classical algorithms that have access to say an oracle data from some system. So there is a sense in which having access to data can add power, computational power. This is, of course, in a rather abstract theoretical setting. There's also been nice experimental progress on this, which was reported here. So that here they're studying, imagining a system where you're sort of accessing the quantum system and entangling it with a quantum computer. And in that setting, it turns out you can sort of rigorously show that there's sort of a type of quantum advantage in the number of measurements you need to do to learn about the system. So it's not a computational advantage, it's an advantage in sampling complexity of the system. But it's still very exciting to see these kind of developments.
And maybe, Michael, if I may just add in, folks, if you want to learn more about this, there's a couple seminars ago we had Robert Wong here and speaking exactly about this, and it was very interesting. So thanks for pointing this out. And I'm also very very happy and humbled to know that the quantum jumps experiment had a seed in your inspiration for this. So.
Yeah, no, it was such a beautiful experiment. I think we're
Thank you, Michael. I'll let you proceed.
Yeah. Okay. So now, actually, so that was sort of the kind of the broader motivation for the talk. I want to talk about more specifically what we were interested in the context of these measurement-induced phase transitions. So now I'm going to start getting more into the main topic of the talk, and that's really, we were interested in understanding this idea of fault tolerance, which is of course well known in context of quantum computing. But one of the essential points in a fault tolerance is that you take the limit of a large system and long time, and you find these phase transitions that just sort of seem to be somewhat generically arise between something you would call success and failure at sustained processing of quantum information. And so the schematic we have in mind is there's some error rate in the system, and below the threshold you have what you could call the success phase, where you successfully process quantum information, and then above the threshold there's the failure phase. And in the context of this talk, we're going to define success rather generously. So it's not the full setting of fault tolerance where you simulate an exact quantum circuit. We're going to be thinking about success as when the output of the quantum system has some quantum information or some memory of the input state. And it doesn't necessarily have to be a controlled process, so it could be a random output. But there's a sense in which quantum information has been sort of remembered or processed by the system. And then we'll define failure as when, the output, even with access to the measurement record that you have, contains no quantum information about the input. And so this is a kind of definition of a quantum error correction threshold. And one of the motivations for this work is we want to understand sort of what simpler physical models exhibit phase transitions of this type, because often the conventional models for fault tolerance are, say, in the concatenated threshold theorem. They're very beautiful models, but they have this special structure which in some sense has fine-tuned elements to it. So we'd like to understand how generic this can be. And so yeah, go ahead.
And maybe I can stretch you a little bit here. And since we had this interesting discussion before the seminar a little bit, some of this sounds a bit reminiscent to these kind of many body localization transitions and so on, where you have some record of the initial state or beginning. I don't know if you'd like to draw some connection or parallel, or maybe we should leave that to the end.
Yeah, that's more. Yeah, I think fault tolerant thresholds are much less controversial than the MBL transition, but in some sense, there is a potential connection if you think from a broad perspective, because NBL transition is a transition in unitary dynamics, but it's a case where that setting, the information is staying localized and therefore accessible by local measurements, whereas above the transition, there's this quantum chaos that arises, and then the information is somehow inaccessible. But because it's unitary, by our definition, it's always in the sort of success phase. That's why this is a very loose definition of success. So you might think of the MBL transition more in the context of complexity theory, where the memory of initial conditions is sort of accessible in an efficient way in the localized phase, and then it becomes inaccessible from a computational perspective in the sort of quantum chaotic phase. But that's that I think we could have a lot of discussion about that. So, yeah, thanks for the question.
Okay, thanks. Thank you, Michael, for that.
Yeah. So what the model that we're gonna that we believe is one example of a model which, in some sense, is a simpler instance of this threshold, are these random quantum circuits with measurements. So they're sort of toy models for noisy open systems, and they were introduced in these two very nice introduced in these very nice papers, and then also studied by a large set of the community. And there's a nice review paper that you can also read about some of it. A lot of the work in this area that's gone on in the last few years. Okay, so the basic setup we have is we have this here. I'm considering a one-dimensional quantum system with time going down. This is the input state, and then we're going to apply random unitaries on this, what we call this brickwork circuit. And after each layer of unitaries, we have just the noise is just essentially measurements in the z basis. So there's some random measurement with probability p at this sort of point in space-time, and as shown here. And so the output is the quantum state, which is conditional on this classical measurement record. And what's been found is that this model, where the tuning parameter, the error rate, is the measurement rate, has this phase transition between the success and failure. So success occurs when the measurement rate is low, so we have fewer measurements, and then failure occurs when the measurement rate is high, and essentially it's collapsing quantum information, in some sense localizing it, actually. Okay, so that's the basic setup and we'll be considering models of this type with variations throughout the talk. Okay, so the first way this transition was understood was as an entanglement transition, and so in that setting, you imagine you have a pure input state and then you have a pure output state because the measurements don't add entropy to a pure quantum state. They just sort of collapse it to another state. And then so entanglement here is you take the output state and you make a bipartition, so you cut it in half, and then you look at the entanglement across the chain. So you look at the two halves of the system, and it was noticed that there's a phase transition in this entanglement where it goes from extensive values, so volume, what we call volume law entanglement, to something more like an area law entanglement, where the entanglement is short range. And you can see that here. So this is showing the entanglement of the output state as a function of the system size. And then above the critical measurement rate, it just saturates to a constant. Whereas in the volume law phase, this entanglement is just growing as the size of the subregion grows. And another very interesting aspect of this problem is that the critical point itself has logarithmic entanglement, which it turns out, which can be understood as arising from some kind of emergent conformal symmetry of the problem. So we believe this is a conformal critical point, and it seems to actually describe a new class of conformal critical theory. So that's been an interesting aspect of this problem. Okay, so now I want to tell you a bit about this alternative perspective on the transition, which is, has closer connections to error correction and fault tolerance. And this is the idea of a purification or coding transition. So the idea is that if instead of starting in a pure state, you can just start in a mixed quantum state, and you can think of the reason that's interesting is that you can think of a mixed quantum state as the quantum state is entangled with some other degrees of freedom, and if the state remains mixed, then somehow the dynamics is preserving that entanglement. And what we found is that this entanglement transition actually seems to coincide with what we call a purification transition, where an initial mixed density matrix stays mixed for exponential times, and then it actually purifies to like a fixed quantum state above the measurement rate, critical measurement rate. And so you can see this type of effect in numerics. So here we're actually studying Clifford circuits, so that allows us to do very convincing numerics on this problem. So that's been another interesting aspect of this set of models, and you can see the behavior I'm describing here. So we started in a completely mixed state, and then we looked at the entropy density of the output state at late times, and you can see that it's sort of staying mixed in this region, and it's sort of purifying to a specific pure state this is the area law phase. And there was some question about whether these two transitions coincide, and we believe that generically they don't actually have to, but in this sort of conventional one-dimensional model I discussed, they're sort of constrained to be the same phase transition because of this conformal symmetry I mentioned, which in the scaling limit you can think of space and time as being equivalent to each other.
And Michael, maybe just to make more high level, like heuristic sense of it. So if the measurement rate P is 1, you're measuring after every gate and projecting yourself to a pure 0 or 1, but it's still a random 0 or 1.
Yeah, right.
And then I guess that sort of motivates why you would expect a pure state as P gets larger. But it doesn't yet tell you that it should be a pure state because you're still scrambling in between each time step and each measurement step, right?
Yeah, right. Yeah, at p equals 1, it's very simple to understand the pure phase, and in some sense this behavior is intuitive, this purification behavior, that it would happen even at any finite measurement rate. And then, of course, zero measurement rate, it's also intuitive. It turns out there's another setting where you can gain intuition, where you have very low measurements. So you have like fully scrambling dynamics and then one measurement. And there you can prove in a pretty simple way that the system will stay mixed. So that's how we sort of arrived at this picture, was using those kind of arguments. And then what really actually turns out, there's currently not rigorous work on this existence of this critical point. And so what really convinced us was this beautiful stabilizer simulations where you can just study, using classical numerics, you can study merged systems.
I see. And just so I understand, purifies at constant rate means that eventually it's going to be a pure state, or is it? What is it?
It sort of approaches a pure state exponentially in time. So it will always be like a little bit mixed, but that correction, that mixedness, will scale exponentially in the depth.
I see. And can I understand that by writing some effective channel that I'm applying over and over again in time, and looking at like eigenvectors, eigenvalues, and like steady?
Yeah, that's a good way. Right. Yeah, thanks. That's a good way to actually understand. To analyze this transition. You can. I haven't talked. There is a lot of work because of the random unitaries. There is a lot of very nice work on connecting these to statistical mechanics models, and what you're describing is you can think of it as the transfer matrix of the statistical mechanical model, and then this phase transition. Actually, this purification transition is like what you said. There's a channel for each layer, and that has a gap in the pure phase, and then the gap closes as you approach this critical point. So it is in some sense it is kind of a gap closing transition in the transfer matrix.
I see. Great.
But it's somewhat unusual object because it's a quantum circuit, so it's not really a classical or ground state problem.
Yes. And the purifies at a constant rate, that's over the ensemble of states, of ensemble of random circuits, or is it also per instance?
It's with high probability over the ensemble.
I see. But there could be some trajectories where that doesn't happen.
Yeah, and it's actually true that there are. So there are rare circuits which don't exhibit this behavior. So there's another. Yeah, this is a rich topic. I mean, there's actually another phase transition that arises when the measurement rate is high enough. Then there's like a percolation transition where you basically cut up this brickwork circuit into little sections which are disconnected because the measurement is sort of disconnected, and then you can very simply understand things because you just have these small, and above that measurement rate, it happens around a half. This is a smaller number. Then the system just breaks up into disconnected pieces.
I see. And I guess another extreme is if you just had single, like Hadamard gates everywhere for the gates, no two qubit gates, and then you're just kind of putting yourself at 50-50 superposition of 0 and 1 every step, and then measuring 0, 1. I guess that would be the other extreme.
And what would that? Well, that might. That depends on. I guess that's true. If that would still purify, but it would, yeah, right. It's an interesting question to think about. Yeah, we pick particular ensembles of gates, but as you start changing the gate ensemble, that all this physics, could change. And I mean, we believe that this is generic in some sense. So if you take generic gate ensembles, you end up with this type of phase transition. But more, it's the usual situation and condensed matter where you have to sort of study it case by case.
I see. And maybe last question, and folks, feel free to post questions in the chat and if I miss your questions, just bring it back up. Last quick question: does the connectivity or topology matter? I mean, here you've picked a kind of very brickwork, nearest neighbor type of coupling, but does the dimensionality, so to speak, or the connectivity qualitatively change things?
Yeah, that's it doesn't change things qualitatively in terms of the existence of the transition, but it's also there's aspects that aren't fully understood yet, and actually, and when I talk about the ion system, I'll move away from these one-dimensional models, and the model we'll study is on an all-to-all connected graph. Yeah.
Gotcha.
So
Thank you.
We'll get there. Yeah. But with that, there's the all-to-all models in some sense are also, they're not fully understood either. So that it's still lots of open questions in this area. Okay, so I mentioned this transition in the purification dynamics, in making these connections to quantum error correction again. It turns out that this type of purification transition is actually equivalent to a phase transition, something called the quantum channel capacity. So if you think of the whole many-body circuit as a quantum channel, then you can show that this type of purification transition is equivalent to a transition in the sort of ability of the system to encode quantum information, which is captured by the channel capacity. And I'll say a few more words about that in the next slide. And so the way you can understand this, so I told you sort of about the phenomenology of the transition. To sort of understand how this process arises, you can use this picture of what we call dynamically generated logical qubits. So you imagine you have your input state, and then you have the initial dynamics of this monitored quantum system. And we're going to think of that as some kind of encoding into a random quantum error correcting code. And what's interesting about this dynamics is that it's able to, in the mixed phase or the volume law phase, it's able to encode information in some kind of optimal sense. Is that optimal in the sense that it protects the quantum information from the future evolution of the system. So you have this initial non-unitary dynamics, and then the future dynamics is actually like reversible unitary dynamics once you condition on the measurement record. And so the way this picture goes is that the dimension of the code space is like the entropy density of this mixed state. So if this is extensive, then you have a finite rate logical code space. And as you approach the transition, this code space, the rate of the code vanishes and it approaches zero. And then, as I was mentioning, so what was sort of interesting aspect of this problem is that below the critical point, this unitary measurement dynamics, it's not just encoding quantum information, but it's actually doing it in some sense in an optimal way, which is interesting from this kind of quantum error correction perspective. And there's been a few applications of this type of idea of like dynamically generating logical qubits. So one is this project. I had a lot of fun, and it was very interesting working with Steve Flamia and Liang Zhang and Stefan Krastanov, where we explored how to use this to maybe make new types of quantum error correcting codes. And then there's also this much more practical work from proposed by Hastings and Haw, where they showed how to do variants of the surface code using similar ideas, which I think is quite exciting. Okay, so now I actually want to move on to start talking about experiments to probe this phase transition. And so previously I was describing this sort of general features of the phase transition, how to understand it. Now I want to get more into how you might actually see this, in a efficient sense. And so what we propose to realize is that instead of taking a completely mixed state, which can be very hard to characterize, you can actually just entangle the system with a single reference qubit. So it's sort of like making a logical code with just one qubit. What we found is that the entropy of this reference qubit actually acts as like a local order parameter for the phase transition. So it sort of very fundamentally probes this critical phenomenon. And you can think of this type of quantity in terms of the entanglement fidelity, if you're more coming from the quantum information perspective. So you think of sort of entangling the reference in some kind of code space, and then you ask if there's some decoding operation at the end of the circuit which can take you back to where you started. And so here, this is again showing the simulations for Clifford circuits, where you see very clearly this sort of phase transition-like behavior in the entanglement of this reference qubit. So as you go to large system sizes below the critical point, it's going to entropy is 1, and then it goes to 0 below the critical point. So this is like the failure phase, and this is the success phase. And the implication from the decoding perspective is that the entanglement fidelity of this reference qubit will converge essentially to 1 below as this entropy approaches 1, and it will converge to 0 above the threshold. And so this is nice because this is a very sort of simple probe of this system, just using 1 qubit, and we'll use that in the ion trap experiment. So another sort of important ingredient in this story is that when you entangle this reference qubit locally, then there's a sense in which there's this idea of emergent information light cone for the system. So this reference qubit is only, if you look at the measurements which affect its outcome, they just live in this sort of light cone-like region of the system. And this is important because, as you might have noticed in the talk, I've been talking about quantum states conditioned on measurement outcomes, which sort of naively incurs some kind of post-selection cost, in the sense that to study some of these information theoretic observables, if conditioned on a measurement record, you might think that you need to get the entire measurement record in the system to repeat itself, and that's obviously takes exponential time. So these kinds of locality results suggest that there's a sense in which not that you can break up the measurement outcomes into those that are sort of important for certain quantities, and you have these notions of locality. And then and that can help in this decoding problem I alluded to. And I should also point out there are some interesting violations to locality in these type of models, because we're doing quantum measurements. Of course you have quantum teleportation, which can transmit entanglement arbitrarily far, and that was explored in this paper.
Could you just explain for us how to interpret the color plot here? What does it mean, the log?
Oh yeah, great. Yeah. So this is time and this is space. So x naught is the position where I entangled the reference qubit, and then I'm looking at which measurement events sort of reduce the entropy of this reference qubit. So and essentially those are the measurements which basically have correlations with the state of the reference. So after you run this circuit and this reference will purify to some particular state, and you want to know which measurement outcomes determine the state of that reference qubit. And when the high color regions are showing you the with exactly that. Sorry, the lights turned off.
I do see your mouse. I see. And experimentally, what's the protocol for measuring, or what? It's from the classical bit strings. You just obtain delta SQ and look at the correlations across them. Is that?
Yeah. So you would it turns out it's experiments. The experiments are difficult, and I'll discuss how we solved it in the case of the ion trap. But what you can think is that like there's a naive algorithm where you build. So we're trying to build, thinking of this error correction analogy, we're trying to build decoders for this reference qubit. And this is saying that to learn that decoder, you only need measurements within this the light cone of the system. And so you can sort of efficiently learn the decoder just by studying certain measurement patterns. That's kind of the philosophy.
I see. Thank you.
Yeah, thanks for the questions. Okay, so now I'm going to discuss this implementation in an ion trap system, sort of a NISQ device, as we like to say nowadays. So this is and the model we'll study now. So we'll move away from this one-dimensional model, and we're actually going to study an all-to-all circuit. So right, so just to give you a sense for this, the circuit we're actually going to study in this setting is shown here. So it consists of random XX gates, long range, and then each XX gate is followed by so this is the definition of an XX gate. It's sort of a natural gate for the Ising system. It's an entangling 2-qubit gate. And then each of these gates will be followed by a measurement with some probability. And this was a nice model to consider because it sort of uses the strengths of the ion chain architecture.
Sorry, when you say start in a mixed entangled state, I'm confused. Is it mixed or entangled, or using it in a different sense?
Yeah, I think you should think of this more as being in a highly entangled state. I think mixed
Okay.
is not quite accurate in there. So it's so this is, we think of this as like a pre-encoding step. So it starts this in a good quantum error correcting code, and then we look at the subsequent dynamics of the system. Yeah, and there's a related work, theoretical works proposing how you might study this in one-dimensional models, which is considered here. But yeah, we're going to be focused on these all-to-all circuits, and we'll actually use some special choices for the gates to make the whole experiment sort of scalable to large systems. Mm-hmm. So just to give you a sense for this particular model has a interesting feature that because we fixed the basis choice for the gate, you notice there's no scrambling basis gates. The measurements along the x directions play a special role. This was helpful for us because we could tune through the phase transition by actually going to very low measurement rates and just changing the basis of measurements. So when we probe the phases in this experiment, we'll be probing along this line from this coding phase to the failure phase. So here we're px is a random choice of the base measurement basis. So if you go back to the previous slide, so this would be a z measurement, and this would be an x measurement. You just append Hadamard's between the two. Okay. Okay, so right, so I mentioned this post-selection problem that arises in this system. So it's natural to ask, like, how we overcome that. And so I'll describe that. Another important aspect of this experiment, this is an ion trap they had 13 qubits, and they don't yet have the ability to do mid-circuit measurements, so they couldn't actually make measurements and then continue evolving the system. And so to sort of overcome that problem, we use this principle of deferred measurements. So whenever we do a quantum measurement of the system, we actually add an extra ancilla qubit, and we sort of keep adding them until we're done evolving the system. And so that overcomes that issue. And then there's this other like box here shown in dashed, and this is essentially making the whole system or the whole experiment scalable to many body systems. So this is actually the decoding step. So what this is going to do is act on all of the measurement outcomes. Here they're stored in quantum states, but that's okay. We have all the measurement outcomes stored here, and we're going to act back on our probe, the single reference qubit, to put it in a particular state. And so you can think of this as a decoder. And what's nice is that for the circuits we chose, we can actually, for any system, we can analytically compute the decoder. So this, again, is using this feature of stabilizer circuits. And this type of problem where you have a reference qubit and it's sort of evolving under this open system dynamics, it turns out to have natural connections to problems people think about in quantum gravity in the context of black holes. So in that setting, you could think of this reference as being thrown into a black hole, and you're asking whether you can decode it from sort of the Hawking radiation that came out of the system. So that's an interesting aspect it's been explored in this work. Okay, so that's the setup. That's how we're going to do the experiment, and then so this is showing our realization of these measurement-induced quantum phases. So what we're looking at is this entropy of this reference qubit, and you can see that in the when you're below the transition, it sort of has a scaling. This is simulations. It scales to high entropy, and then below the transition, it scales to 0. And here's the experimental results shown here. So we were able to go up to system size 8, and these are the theoretical predictions, and this is experiments. So you can see that we have a really nice theoretical understanding of the system. And you see this sort of scaling behavior we're looking for, where below threshold, the entropy goes to 0, and then above threshold, you sort of information is staying encoded. So we were very excited to take this data, which for the experimentalists was a really huge effort to in sort of programmable quantum systems to be able to implement models of this type. And this is a technical point, so we used a simpler type of entropy measurement to realize this phase transition. Okay, so another aspect we'd be interested in is to actually probe so there we were just realizing the phases. We'd also like to be able to really probe the critical point of this model. And we have a proposal for that by looking at, it turns out if you look at the decay rate of this entropy versus time, that's actually a sensitive probe of the phase transition. And we think that with modest system sizes, you could really start to see this critical point emerge and its universal scaling properties. There will be, experimental improvements that need to be made along the way. So particularly these mid-circuit measurements, scaling to larger systems, and then also being able to do deeper circuits. But they tell us that all these things are on the way for them, and I think many experimental groups are moving towards these types of capabilities. And I think that's really nicely highlighted by this result from actually academic groups working on an IBM machine, I'm sure using Qiskit. They were able to study the one-dimensional version of this problem and actually probe the critical point. And in that case, they used a full quantum state tomography. So it's not necessarily scalable to large systems, but it's very impressive experiment. Okay, so what I want to talk about next is some of our progress in this problem, and I guess in the last few minutes of the talk, on sort of moving beyond stabilizer circuits. So in all the work I discussed in this protocols for probing the phase transition, they were really using this special properties of stabilizer circuits, which you can simulate classically. And these are nice because they're actually experimentally accessible. They're a natural gate set to consider because of their roll and fault tolerance. Their dynamics are very robust to noise because they have this kind of discrete behavior. So we use that in the analyzing the ion experiment. And then, as I mentioned, they also have efficient decoders using this, say, the Gottesman-Mel theorem. But as is well known, of course, the gate set of the Clifford group is non-universal, and it's actually been found that if you study these phase transitions with more generic circuits, say where the gates are Haar random, it turns out it's a different universality class. So this was shown convincingly in this work here with Jed Pixley's group at Rutgers, where we were able to really push the numerics for his group was able to really push the numerics for the exact numerics for generic circuits to show a separation in the critical properties of the two models. And so it would be nice to study these more generic systems in experiment, but the issue that you run into is this sort of post-selection problem, or said differently, you have to find efficient decoders for dealing with these non-Clifford gate sets. And so that brings me to this idea of this neural network decoder, which I alluded to in the title of the talk. And this is kind of work in progress, but we think it's in one exciting direction to really push these types of models to much more accessible, much more accessible in experiment. So what we're going to do is treat this decoding problem I mentioned of the reference qubit as a type of image classification problem, and then we can port over tools from machine learning to just treating it in that setting. And so the reason the connection to image classification is you have this reference qubit, and we're just essentially trying to do tomography. So we want to learn after the circuit, we want to learn its expectation values in the poly X, Y, and Z basis, and that's going to be, those values will depend on the specific measurement records you saw. So each measurement record is like an image, and we want to associate it with like an expectation value for these poly operators. So that's how we were able to use that connection. And because of the sort of locality of the circuit, that gives you the spatial structure. So that's the idea. And the nice thing about this approach is that it only uses the results of the quantum measurement as input. So it doesn't know anything about the circuit. So that's a nice feature. And so it sort of works in settings where you have, say, coherent errors in the system, or you have some unknown Hamiltonian evolving the system. So that was sort of interest to us to find algorithms of that type. Of course, and this is, a downside of our work, because of the difficulty of generating data on large systems, we first just benchmarked our algorithms on stabilizer circuits where we could really understand things well. But there's a lot in common with generic circuits, so we think this will generalize beyond stabilizer circuits. And so, just to give you a sense for how the evolution occurs in stabilizer systems, so you have this. We're studying this entropy of the single reference qubit, and it purifies at a particular time. And so what we're doing is essentially searching for that, there's sort of one measurement which collapses the entropy. And so when we do this decoding, we're essentially searching for that measurement outcome. And what I'm showing here is how the purification time scales in the different phases. And what you can see is that in the area law phase, things tend to purify quite rapidly, so an exponential time. And then another interesting feature is that in the volume law phase, there's sort of a rapid purification process that occurs, and you can sort of efficiently learn that aspect. But then there's much later purification times which don't show up until exponential time. So that actually gives you a somewhat efficient approach to learn this behavior. And then what's maybe sort of intuitive is that the critical point is actually the most difficult point to learn, because the dynamics, the purification can happen anywhere on a large scale. And so this is showing the scalability, so the number of training samples we need to learn this behavior. And you can see that it's if you fix the purification time, it's actually scaling favorably with system size. So it's not, as you scale up to much larger systems, it's not becoming more difficult to learn. And this is showing the performance of our learning on these type of dynamics we're interested in studying. So you can see that at sufficiently early times, we're able to learn the entropy efficiently. And we did some basic attempts at critical scaling to see the phase transition, and we think this is a promising approach. And then and I'll just say a few words about scalability. So why this type of learning approach is scalable in some sense. And so what we did is so imagine you have a full circuit, and you want to know if training it on, if you sort of train your decoder on a specific circuit, will it be generalized to much larger circuits? So what we did is we looked at, we sort of trained the decoder on sub-circuits of much larger circuits, and we were able to see evidence that that things scaled well. So especially since I'm running out of time, I'll sort of wind down the talk here, and I can take questions afterwards. So just to give you a summary of what was discussed in the talk. So first, I told you about this sort of fundamental link between these entanglement transitions and monitored quantum systems and fault tolerance thresholds. There are these nice applications to dynamically generated quantum error correcting codes, which we explored in this work, and we're continuing to explore. And then a lot of the talk I focused on how you might study this physics in sort of current day devices. And so we think these sort of local probes give you sort of efficient ways of studying these phase transitions. And I told you about applying this idea to an ion trap system with 13 qubits. And then I talked about this sort of exploratory work we're studying on using machine learning to maybe give you a different route to studying this physics in experiment. So just to end with some of the open questions for this work. So in general, you know, I've talked a lot about these specific models. We would really like to move, you know, to more generic systems to study really the robustness of this type of behavior to realistic errors and noise, uncontrolled environments, and there we think that using things like error mitigation, which IBM has really pioneered, will be crucial. But then also potentially tying in ideas from active error correction is also promising. And another question opened up by this work is, you know, that this dichotomy between success and failure might be too simple in some sense. In these models, we're seeing huge number, and I didn't discuss this work in this talk, but it's in, you know, in some of the recent papers on this topic. There's really a huge number of phases that arise in these systems, and we'd like to understand if there's more than one way to quantify success in these settings. And then, you know, another aspect that this work is pushing on is this idea of understanding phase transitions in the context of fault tolerance. I mean, we usually think of trying to go deep below threshold, but it's potentially of interest to work sort of near the critical point, and you can ask whether that's a practical solution for scaling up quantum information systems. So with that, I want to really thank you for your attention, and thanks. Thanks,
Michael. Thank you for the wonderful talk and very interesting results. I know we had a lot of questions during the talk. There's a couple now in the chat, folks. Feel free. This is a great time to post any final questions in the chat or bring them back up. Maybe the first, there are a couple questions, and we do have, maybe we can use some of the time. Did you skip a few slides at the end?
I didn't skip any slides. I just went very quickly through them. So.
Okay, so we may come back to that, but let me bring up the first question from Shashi here. Could we have, this is going back to the reference state, could we have more than one system qubit entangled to more than one reference state? How will they affect each other's light cones? How will that affect measurements? Yeah,
that's a great question, and we did study that. It turns out adding two reference qubits. So the one reference qubit probes the order parameter for the. So there's some like putative underlying StatMech model that we believe describes these systems, and this reference qubit probes the order parameter operator. So if you think of the critical point, there's sort of an order parameter operator, and if you use two reference qubits, it turns out it probes like 2-point functions of the order parameter. So you can think of order parameter would be magnetization, and then the 2-point function would be magnetization on one site correlated with a different site. And so that's fundamentally what that quantity probes. You do have the issue that as you go beyond the single reference qubit, the decoding gets much harder. So we don't know if that's, we haven't thought about trying to develop efficient decoders for two reference qubits, although that's something we should consider. I would suspect you could leverage some of this light cone arguments to study that. Yeah, it would be interesting. Yeah, thanks for the question.
Good. That's a great question. Thank you. It sounds like maybe an open area for research in next steps. There's a question from Old Baz. Something that helps improve, so this is to the decoders neural nets, something that helps improve image-related neural networks is data augmentation, for example, rotating, scaling the images, etc. Does that potentially come into play here? Have you tried or thought about anything in this direction?
Yeah, so that's the thing is I'm new to, you could probably tell I'm new to this machine learning in machine learning in practice, and so yeah, I haven't thought about that, but that sounds like a really interesting idea. Yeah, I can definitely see how tricks like that could help. Yeah. But yes, I guess the answer is unfortunately we haven't thought about that direction, but sounds like we should.
Great, thank you. And then Shashi has a follow-up or second question. Will it always be possible to design UF analytics when system is scaled to very large number of qubits? So it's a question of scalability.
Yeah, so for the Clifford circuits, that's the case. You can use like this feedback circuit is like it's like a Boolean. It's like a circuit of C-naught gates that's doing certain Boolean logic, and that can be solved efficiently. But then, of course, once you go beyond, once you add non-Clifford gates, that's no longer possible. I can tell you some work in progress we're thinking about along this direction. So instead of looking at it's also inspired by machine learning. Instead of looking at this reference qubit, you can just imagine you have your monitored system and you take all this measurement data, and you can ask if there's a sort of classical Hamiltonian, like a classical StatMech model that describes the measurement outcomes. And so we've been using these tricks of Hamiltonian learning to understand that question. And I can tell you, yeah, I guess I'll say more about that in future work. But there you would be using like one example in machine learning would be restricted Boltzmann machines, which essentially solve this Hamiltonian learning problem in some settings. So that would be another potential connection that we're exploring.
Excellent. Thank you, Michael. I'll mention there's some more discussion in the chat about convolutional neural nets for image-related work and so on, but I think maybe we touched on that already. Great. I think, yeah, seeing as we're almost 10 minutes over, I think this might be a good time to think of if you'd like to share any final messages with us, and then we'll do a closing afterwards. Yeah, don't log off immediately. We debrief and then we'll log off.
Okay,
yeah.
great. Yeah, I mean, I should say that this experiment with the ion trap, that I think the ion system, they use Qiskit to control, like the way that Pradeep tells them the circuits is he gives them a circuit in Qiskit, and then they compile that. So Qiskit has been instrumental in sort of making this this type of work sort of easier for academics, I would say. So so thank you for your efforts there.
Yeah, big kudos to the Qiskit team, and they're helping make the seminar possible right now. You can't see David, folks, but he's in the background here. So he's making this run smoothly, and I'm really glad to hear that. Yeah, I actually ran into Pradeep several times, I think, in March meetings, so that was really nice. And if he's watching, it's really nice work. So folks, well, maybe I should say, Michael, thank you for accepting our invitation. This has been really wonderful talk. Folks, if you missed anything, you can subscribe to Qiskit, go back and rewatch the talk, and to stay up to date on the latest in the quantum ecosystem and quantum research, tune in next Friday and every Friday after that at noon Eastern Time. Thank you for tuning in. It's been a pleasure.
Thank you.